You know, the Aaronson video is really good lecture in complexity. I mean, for anybody who hasn't learned complexity, Scott Aaronson, there it is. This is a really good introduction to complexity, which I think, you know, is basically all people need to know to understand quantum is just study 20 minutes of complexity. And Scott explains it really, really well.
Feynman and Deutsch had that led to the idea of a quantum computer was, well, if nature is giving us this computational lemon, then why don't we make lemonade out of it?
Here he tells a very good story about a very interesting theorem, but I think we can skip it. Yeah, the 𝗪𝗩𝗪 theorem. So here is maybe one of the best explanations of complexity from one of the most knowledgeable people on the field. Take a listen.
Maybe if we can get into like the foundations of the complexity theory.
Okay.
You already mentioned the P equal NP.
P means polynomial time. So it's the class of all the problems that have an algorithm to solve them running on a standard, deterministic digital computer like the one that we're having this conversation on right now. And what polynomial time means is using a number of steps that increases only like the size of the input, the number of bits in the input raised to some fixed power. Okay, so the context here is that complexity theory is the field that tries to classify problems by the inherent resources needed to solve them. Like how much time, how much memory, how much randomness, or quantum computing resources, or parallelism, and so P and NP are two of the most basic classes that we study. We care, not just about like the raw number of steps, but typically about the scaling behavior. As you go to larger and larger inputs, at what rate is the number of steps that you need increasing? Okay, so what we like to see is, often the gold standard is linear scaling, right? Which would mean when your input is twice as large, then your algorithm takes twice as long.
So that's the idea, briefly, is that you have polynomial time algorithms and you have exponential time algorithms. This is super easy to understand, or it should be super easy to understand. And you can see there's a very, very big difference between 2n squared and 2 to the n. Shall we do some basic calculations? Well, in a polynomial time algorithm, if the input size is, say, 10, I'm stuck with the Elon voice, impersonating him. You know how your mother always tells you when you're young, if you make that face, your face will be stuck like that the rest of your life. Well, if you impersonate a voice enough, you start sounding like the voice. So anyway, here's a 10-bit length, let's say, or whatever. It doesn't matter. It's bits or bytes. Or in our polynomial time argument, it's 10 squared, which is 100. So we need 200 steps here. 200 steps, which is for an input of 10. How about for exponential time? Well, that's 2 to the 10th power. Does anybody know what that is? Is it 10 to the 24 or 1024? You don't have that right? 1024? You might look at that and say, oh, that's not so bad. It's 5 times longer, but it can't be that bad. I can wait 5 times longer, 5 seconds versus 1 second or something like that, right? Okay, well, let's do 20. All right, well, 20 squared is 400 times 2 is 800. So that's not so bad. We doubled the size of the input length, and the time it takes to calculate this went up 4x. Make sense? Okay, but what's 2 to the 20th power? I can just ask Wolfram Alpha or something like that. 2 to the 20th is around 1 million. Well, that's a big, big difference. If these took, shall we say, I don't know, 1/10 of a second each, maybe even 10 milliseconds. That's not so bad, right? For an operation, 10 milliseconds. Well, that would be 2 seconds for this guy, 10 seconds for this guy. Is that right? Do I even have that right? 2000 milliseconds is 2 seconds. This would be 8 seconds for a longer input. Let's say you wanted to, calculate, let's say you want to factor an integer. If you had a polynomial time algorithm for factoring, one does not exist. You could do that in 8 seconds, but here we'd have a big problem. This is a lot of seconds. It would be 10,000 seconds, which is how many minutes? It's 174 minutes. So 3 hours roughly. So we've went from this, which only went up 4x, to this, which went up quite a lot, very exponential, from 10 seconds to 3 hours. And you can imagine at 30, I can calculate this in my head. Again, 30 times 30 is 900. 900 times 2 is 1800. 1800 seconds is milliseconds. Or I guess if one operation takes 10 milliseconds, this whole thing would take 18 seconds. Again, not bad, but let's do the math for 2 to the 30th power. That is a big number. Well, that's a lot of seconds, right? So let's divide by 60. And this is how many minutes? Well, that's a lot of minutes. So how many hours is that? Oh, that's a lot of hours. So how many days is that? Well, that's a lot of days. How many years is that? So this calculation would take 34 years. Do you see the difference between an exponential and a polynomial algorithm? I'm trying to make this as simple as possible, 𝗪. So again, the exponential algorithm is 2 to the n, very simple. 2 to the n. And the polynomial time algorithm is 2n squared. And you might say that goes up fast. 10 input size, 20 input size, 30 input size. But you can wait 18 seconds. You can't wait 34 years for a calculation to finish. And in fact, when we look at Bitcoin, it's 2 to the 256th power. So if I did a 256 as my input, again, 256 squared is, I should know this, 65,536. It's a number most computer scientists know. And then I multiply that times 2. So that's 130,000. Again, this is you can wait this long. That's 1,300 seconds. It's not bad. But 2 to the 256th is 10 to the 77th, which is the longer than all the time in the universe, by a very far magnitude, actually. That's enough for many, many universes. So no real way to calculate this, right? Wrong. There is a way. Peter Shor theorized that if you had the resources of a quantum computer, you could do it very quickly. You could change from exponential to polynomial time. You could swap categories. That's a really big deal. For which problem, though? Only factoring, as far as we know. Factoring has a sister problem called discrete log problem, which I spend almost too much time on. But in general, it's a similar kind of problem. And this is why we use factoring for cryptography, because it's impossible to do this calculation. So you're safe, right? You're safe in terms of doing factoring, or making factoring the basis for your cryptography, because there's no actual way to factor a number that big. And that's not even that big. It's a 77-digit number. But there's no way to do that right now. It's impossible. But a quantum computer could do it quickly. But a quantum computer can't do any other problem quickly. That's the part that we tend to forget. And the only problem that it can do quickly from a computational theory perspective is when you go from E to P, but there has to be a reason. You're switching complexity classes. And the reason for Shor's algorithm is very clever. Peter Shor will go down as one of the most brilliant people in the world for figuring it out, but there are no other Shor's algorithms. So this is all we can do quickly, is factoring. But unfortunately, the world of computing is way more than factoring. There's all kinds of problems like sorting, which is a pretty big one in computing. Even things like summation, it's not factoring, right? Increments, copying, all of these things have nothing to do. I mean, we can go on and on. There's thousands of algorithms, maybe even more than that. Factoring is just one thing. But it turns out that you can factor very quickly on a quantum computer. But what else can you do on a quantum computer? Well, not a whole lot else. far as we know. There's no real product here. And that's kind of the theory behind the short. If you can't do anything on these machines, then what's the point? Why have a quantum computer at all? And that's kind of where I'm coming from. Doesn't make any sense. It's just a bunch of garbage, really. And again, we're in a current era where we have meme coins. Bitcoin's worth trillions of dollars. This is an era of investing. We may return to an era that's a little less partying, a little more sober. But right now, you know, the environment's quite good and quite wild. But until you can make more algorithms that actually change the complexity class, you're not in good shape. Now, why? Why is that the case? Well, why can't a quantum computer just be faster, right? Well, we know that Shor lets you morph an exponential problem to a polynomial problem, but let's just compare a polynomial problem against a polynomial problem. So let's say you have some sorting algorithm. Okay. And the sorting algorithm has complexity time of the square root of n. Okay, so this is a polynomial algorithm. We're going to compare classical versus quantum. Well, what goes in to running speed? The first is something like gate speed. The next thing would be something like memory to register file. The register file is the fastest part of the computer. Then you have the caches and so forth. So I'm going to ChatGPT, what is the gate speed of a transistor-based gate? Quantum theoretically could break cryptography, yes. Amazingly, it says here 30 picoseconds. Remarkable, 30 picoseconds. Pico is 1,000th of nano, so quite fast. Some are in the nanosecond range, so 1,000 pico is 1 nanosecond. Some even have less than that. Let me ask it. Let's try a gate speed for a superconducting transmon qubit quantum computer. Okay, somewhere between 10 to 300 nanoseconds. So it's certainly slower, anywhere between 30 to 10,000x slower than transistor. And we're going to add fidelity here, which we know is 99. Well, we can do 0.9 to the what? 0.9 with a bar over it, I guess, to the 10 to the what? Negative 18th or something. Whereas for quantum, it's only 0.9 with a bar over it. Well, if you ask Rigetti, 10 to the 2, not even. And then finally, how fast is our clock speed? That's the gate speed. Clock speed, we all know the clock speed of computers right now, they're around anywhere from 2 to 5 gigahertz. The clock speed, well, yeah, these gate speeds compound. So yeah, it kind of looks like 1 to 10 megahertz, which we've talked about. I actually think it's slower than that, but ion traps are 1 to 100 kilohertz. So it depends on whether you're ion trap or superconductor. And there's no register file or RAM or anything like that in quantum computing. So you have to build the entire circuit from scratch. Now, again, will that change someday? You know, maybe. But for now, there's none of that. So there's no disk. There's no anything like this. So you have this problem. And I guess finally, probably the most important thing is, you know, what's your sample? Well, we have a 135 qubit machine at IBM, but how many transistors are on? How many transistors in Intel's latest chip? Look at how crazy this is. 44 billion. Okay. So if you have the quadratic, if you have the exponential speed up, quantum computer wins. It would take until the universe freezes over versus just, what is that? 1300 seconds is not very long at all. 20 minutes, not bad. Better than the universe freezing over. But there's only one problem that this, unfortunately, otherwise quantum would be awesome and really cool. But unfortunately, there's only one problem where you get this, which is factoring large numbers, which isn't really interesting or a business. So if you had to do quantum heads up against the classical, well, let's start with the number of gates. Well, like I said, on an NVIDIA or an Intel chip, I've got 44 billion gates, not bad, or 44 billion transistors, which can sort of act as bits. Well, on a quantum computer, the best one we've got has 135. So needless to say, the quantum is a bit outmatched. Why in the world would you ever use it? You wouldn't. You would only use it if you can get that crazy speed up. Okay, well, let's keep going. What about clock speed? Maybe it's a lot faster. The latest AMD processor can do 5 billion cycles a second. Quantum computer, even the fastest one, can do 10 million cycles a second. Again, vastly, vastly outmatched. So you're outmatched by many factors in virtually every department. There's no place where quantum can win because it's a new technology. How about gate fidelity? Well, one is 99.9, and then one is 99.999999999 and some more nines. So how in the world would anyone in their right mind think that you could match classical versus quantum? You couldn't. This case should more or less be closed. The only way you could do it is with that special algorithm, right? Some way to get from this world of complexity to the next. So now let's talk about why there would be this illusion that maybe this is not the case, because this is pretty sobering indeed, right? I mean, there's no kind of way out of this logically. It's just kind of over. So why would there be a potential way, or a misunderstanding really, of this? Well, there's a few things. What about the current business, right? I mean, these companies don't have much revenue, but somebody's paying them something. Right? Well, let's look into that very closely. I'm using Gödel. I'm going to do EM for earnings matrix, sales. Okay, so before this, the companies started messing around with their accounting, let's look at a typical year for somebody like IonQ. I'm going to talk to you about the accounting stuff. But IonQ's revenue is 11 million. But the problem is most of these were grants. None of this is product revenue. This is just investigational revenue. When a customer does show up, it's largely out of curiosity. Sometimes the work's done for free, but you're talking about $100,000 style proof of concept work. If any of these graduated to serious production, the revenue would be billions. But if you talk to people who have used these things, they'll tell you the same story every time. We don't use it, the proof of concept failed. We'll check back in a few years, we'll do another proof of concept. We're always looking for new technologies to help our business. If it's a $100 billion business, right? We don't want to miss out on a proof of concept that might be really exciting. But unfortunately, the proof of concept never materializes into a real company. What IonQ has done, so each company has a different way of lying. What IonQ has done is they've gotten more grants and they've acquired companies that either have more grants or non-quantum businesses to make it look like their revenue is growing. But if you ask anybody if they're buying more quantum computers or using their cloud more, it's not the case. How about Rigetti? Let's go to Rigetti. Rigetti is the only other serious quantum computing company that's public. And they're a little bit more honest. They chase these grants less often, and they don't fake sales and doing acquisitions to do fake sales and things like that. Well, Rigetti's revenue is bad, and it's declining. So their revenue is only 8.7 million. And last quarter, it was a mere 1.47 million. Gödel, which is not worth many billions of dollars, has revenue in that ballpark. Gödel's market cap's not many zeros, but at least 1 zero removed from Rigetti's. So, pretty pitiful number here. So Rigetti is actually maybe one of the only companies that's honest. Okay, then we have QUBT, whose revenue last quarter was $35,000. Again, there's no other than doing Shors, where are you going to work here? There's no place to actually succeed. And then we get to the curious case of D-Wave. D-Wave has almost no revenue as well. They did sell one computer, but if we strip that unusual one-time sale out, revenue, it's been around 7 to 8 million. Again, this is about as big as you can make a company that doesn't really sell a product. You see the same number appear over and over again. D-Wave, Rigetti, IonQ was a little more aggressive in chasing that revenue, but this revenue isn't going anywhere and the products really haven't changed. So the revenue is not growing dramatically. If anything, it looks like if you take out that contract or that one computer for D-Wave, maybe the revenue is actually dropping, which doesn't make a lot of sense. So how in the world, you know, without the complexity speed up and without any revenue growth, where are you coming from? What's the lie for D-Wave? Well, D-Wave is basically an optimization shop. Optimization is a funny thing. There are many ways to optimize a process. And if you look into optimization, it's a vibrant field. And one of the main pieces of software, for example, that's used there is called 𝗪𝗏𝗘𝗢𝗓. And there are many other companies that will go into your business and say, okay, we have identified a business process we can speed up. We can do an optimization. We can run an algorithm that will actually make this a lot faster. And in fact, we do this all the time in our code base. If we see a process is exponential, we want to move it back to polynomial if we can. And in fact, you don't need any kind of new computer to do that. In fact, you don't even need 𝗪𝗏𝗘𝗢𝗓 software to do that. You just need a careful eye, and you need to go through the code base and find a place where you're using a manual process, an exponential process, etc. And you basically say, okay, well, we can move this to something else. We can move this to, you know, a polynomial time process. Or we have a faster polynomial time algorithm. So if you're an optimization specialist, this is what you do. In fact, companies hire optimization programmers all the time. We do it all the time. You know, one of the difficult problem is drawing components on the screen of the web program. And Facebook made a fantastic library for this optimization called React. They didn't need a quantum computer. It's not very hard to run, but it was a bit of a clever optimization trick. So the way I look at D-Wave is that it's basically an optimization company that's sort of masquerading as a quantum company. And their quantum technology, it's not actually used. It's simply a company that is doing optimization work for clients. But optimization companies exist everywhere. Accenture, IBM on the big scale, and much smaller companies, including single consultants you can hire on a smaller scale. So D-Wave hunts for optimization business, and they're not very good at it. They only have a couple million in revenue. And quantum is their hook. But the reality is they find very normal optimization problems that anybody can solve. ChatGPT could solve. In fact, ChatGPT is very bearish for quantum, for at least for D-Wave quantum, because you can simply ask ChatGPT, hey, I have a list of employees, you know, what's the best way to schedule them? Well, D-Wave will lie to you and say, well, you need our quantum computer, we're going to charge you this much money for it. But the reality is it's something as simple as, well, you're using this kind of algorithm, you should shift it to another one. And again, I'm trying to do a D-Wave demo where I can show that their quantum, quote unquote, quantum optimization tool isn't any better than any other tool. And the reason this is important is because there is no speed up. There's no theoretical basis, right, for that quantum speed up from exponential to polynomial. We know that it exists with Shors, but there is no speed up. That's how you know it's a fraud. There is no speed up. The number of quantum algorithms is very low. There's only a handful, and none of them are about this, the QBO algorithm. Q and QBO is not, by the way, quantum. It's quadratic, unconstrained binary optimization. And you can do QBO on regular old computers. In fact, I think regular old computers are faster for the reasons I showed a moment earlier. They have faster speeds. I think that the quantum, in fact, one undercover D-Wave employee said, the quantum part about what we do is just snake oil. It's just a way to get the optimization business. It's not actually part of the process or used very much. You know, so if we can find an optimization, let's say the customer has something that takes, I don't know, 300 hours to do. And we find an off-the-shelf pip install package, Python package that takes that to 30 minutes. Guess what? The client's thrilled. But things like this happen all the time in computer programming. You guys ever see me hacking away at a program? Oftentimes I will find a program that will speed up my work by 1000x. For example, if anybody knows programming, simplest thing in the world, and maybe one of you can answer this pop quiz. If I had this one program, let me just show you one program, very simple program. I'll do it in like sort of a pseudocode. Program A and program B, tell me the difference between these programs. I have a for statement here for I equals 1, I less than 1 million, I plus plus, and then we have, in the statement here, we'll do, let's see, here we'll declare n is 0, and then we'll do something like n equals, I don't know, 2 plus I. It's a silly algorithm, but we're going to do it this way. And we're not even going to, we're just going to do next I here. Okay, and then at the end, we're going to print I and print n. This is very poor programming, by the way. So here we'll do the same thing, except we're going to reverse the order a little bit. In this program, over here, I'm going to take the print statement and I'm going to switch it with the next statement. What's going to happen to my runtime? B is faster, you think? Yeah, it would slow a tremendous amount. Why? It's going to be extremely slow. Well, it will compile. I just have to move this print statement over here. Yeah, so the print call is extremely slow, right? The print call takes a huge amount of time compared to the addition. It's probably 1,000 times slower or 10,000 times slower, right?